So unfortunately, I forgot the pen for the computer, so I won't be able to draw. So let's see if I can. Okay, so I think I can just use this picture. So this is the front view of a wing, and the loss of lift at the wingtip and the increase in drag is due to these vortices, right? So I won't be able to draw nicely with the mouse, but so there are these vortices here, and if you can somehow reduce them, you cannot eliminate them completely, but if you can somehow reduce them, you will get a big benefit in terms of aerodynamic performance. That means you will have more lift force and less drag force. So one way to do that is to use winglets. So that's why the aircraft manufacturers use winglets. And if you think about what a winglet is, you basically put a blockage here, right? So if you put something like this, that's how a winglet looks like, right? Or it can extend on the lower surface as well. Then these parts will prevent some of this flow here, and that will be reducing that. But this phenomena, these wingtip vortices, can be eliminated if you are flying very close to the ground. So if the aircraft is flying very close to the ground, suppose that this is where the ground is, then the air on the lower surface will be squeezed here, and it will these vortices will be smaller, right? If you have ground here, you cannot have such large vortices created at the wingtips. Plus, there will be air squeezed underneath the wing here, and this squeezed air will be increasing the pressure under the wing. So this phenomenon is known as ground effect, and aircraft flying in ground effect can have huge performance increases. So I would like to show you some videos related to that. So let's start with this video. So here they explain what this ground effect is, and they show some sample aircraft using this phenomena. This is actually an advertisement of a company. So they brand an aircraft and they explain how good this thing is. So let's watch this. So anyway, I don't think we need to watch the entire video, but if you notice that it says you can get a performance increase up to 250%. So that's a huge improvement. So that's how bad this wingtip drag effect is. And by flying very close to the ground, you can eliminate that problem, and that's a huge improvement. And in fact, this concept is not new. So as far as I know, first Russians figured this out. They thought that you can get the benefit if by using the ground effect. And let's see their example. They were flying. In fact, they made really huge aircraft using the ground effect. So let's watch the second video.
Front engine roared the line, propelling the KM forward and out of the water. At 540 tons, it was 150 tons heavier than the future Boeing 747 and larger than a B-52. The tail was 5 stories high. It was by far the biggest and heaviest creation ever to take off. But a week ago, the test pilot, it was a memorable day. The first flight was a resounding success, and hopes ran high for the KM's military applications. Later tests proved it could fly at more than 400 miles an hour. There were no press announcements of the KM's maiden flight, or any other Ukraine-land flight. Everything about it was hidden behind an impenetrable veil of secrecy.
So I don't know why there is such a horrible music to this nice video. I think the person who uploaded this to YouTube edited that. I don't think the original documentary had that music. So anyway, this was a secret aircraft. So the Western world didn't know about this aircraft for a pretty long time, and they were using this in the Caspian Sea. So I don't know how successful it was commercially. I really don't, but I'm sure you can easily find the answer if you Google it. So there are a few things I would like to point out regarding this airplane. So you heard that right? It is even heavier than the Boeing 747 and larger. It's a huge aircraft.
And larger than a B-52.
So I don't know the fuel consumption. It would be really interesting to see how it compares with Boeing 747 in terms of fuel consumption. But it should be considerably better.
By far the biggest and heaviest creation
So I'm looking for a nice view. Okay, I think it's a nice picture. Let me So if you look at its wings, the aspect ratio is quite low. So from what we know, if you try to fly this airplane high in the atmosphere, it would be a very, very bad, you would get a very bad performance because of this low aspect ratio wing. Right? So it's rectangular and the aspect ratio is really low. And normally again, if you try to fly this up in the air, due to these vortices, you would be getting a lot of increased drag. But since it's flying close to the ground, you don't get that bad aerodynamic performance, and that's why how it becomes very efficient. And now the second thing I would like to pay your attention to is the tail. If you look at the previous examples as well, they all have a very large horizontal stabilizers, and that's because you need to have a pitch-up moment to experience this ground effect. You need to have a certain positive angle here so that the air will go in there, the air will be swept under the wing to create this cushion effect. And for that you need a large horizontal stabilizer. So that's what's common with this one and the previous designs. Okay, and let me see, there was another one. So this is again like an advertisement for another company.
Once it's in its flight mode, that's because the air pitch is a ground effect machine, something utilizing that well-known phenomena. When a wing approaches the ground, it experiences increased lift and reduced drag. The air-efficient ducted fan provides forward propulsion, skipping the craft along on its sponsons like some new trimaran. But as it accelerates past 25 kilometers per hour, the ground effect creates lift, and at 65 kilometers per hour, it takes off. To make this happen, the flare wing deflects air downwards, which bounces from the surface of the water, and so keeps the craft flying. Its cruising altitude is only 1 meter, so it stays in this ground effect region, and doesn't suffer the increased drag experienced by conventional aircraft flying higher. There's no drag from the water either, as it's not in contact with the surface. So the airfish can cruise with minimal resistance and maximal fuel efficiency over water, land and ice. Its physics, learned from understanding how heavy seabirds can glide effortlessly, but only when close to the ground or water. The lightweight composite, aluminium and Dacron construction means it weighs only 500 kilograms. Its cruise speed is 120 kilometers per hour, and by the time you come down to Earth again, your heart rate is about the same. But unlike an aircraft, the 45-litre fuel capacity gives an astounding range of 300 kilometers, achievable because so little friction is involved. The engine is a conventional 70 horsepower German motorbike one that needs only
So again, in this video they share some numbers claiming how efficient it is. So with a very small power, you can travel at large speed and by consuming very little fuel. Okay, and I have one last video regarding these ground effect vehicles, and this is about small models. So anyway, I will share these videos with you, and you can find much more videos on YouTube if you're interested. And there was even a video showing how to make such airplanes out of paper. So if you're interested, you can watch that one too. So basically you can make a paper airplane that will float over the ground like this one. So even actually this test demonstrates how efficient this design is, right? So in the powered versions, it's not easy to appreciate that, but I think this one is, you can very clearly see that with a very gentle push, this aircraft flies over on the floor very smoothly for quite long distance. So obviously, if you can fly very close to the ground, it would be a very nice thing. But unfortunately, you can't always do that, right? I mean, imagine that Russian huge plane flying over the sea. Imagine that crosses its path with a big ship. You can't easily avoid if you see an obstacle, and it could be disastrous. And obviously, for calm weather, if the weather is nice, can be a nice thing, but if you can't really travel that over the ocean where there may be huge waves. So anyway, so for a lot of reasons you have to fly above the ground, and if you are doing that, then you have to deal with these three-dimensional losses. Okay, so anyway, so this is what I showed at the very beginning. These are the four forces of flight. And to calculate the performance, we need to know about these forces. So these will be, in the majority of this course, we will be considering these four forces. And to be able to make performance calculations, we need to know all these forces, right? So weight is the easiest one. So you know the weight of your aircraft. But you need to calculate all these three forces so that you can calculate the performance accurately. So for lift and drag, these are our equations. So this is the dynamic pressure. And the important parameters here are these lift and drag coefficients. And they depend on the design of the aircraft, which is normally fixed while you are flying. And while flying, the coefficients can change due to pilot control inputs. So if the pilot plays with the elevator or the ailerons or the flaps, he will be changing the values of these coefficients. And these coefficients will be, the forces, not the coefficients, the forces are changing as the speed of the flight changes. And this fact is included in the dynamic pressure term. And also you need to pay attention to the Reynolds and Mach numbers as they change these coefficients as well. And so during a flight, except for the pilot impulse, the most important factor that causes the aerodynamic coefficients to change is the angle of attack. So during a flight, the most important parameter that causes these forces to change is the angle of attack, and that's so that we will be talking about how it affects these terms. So basically, so anyway, let's come to. So this is just a summary of the previous discussion. For a two-dimensional airfoil, nothing changes along the span-wise direction, and this is the 2D scenario. And in the three-dimensional case, you have some span-wise flows, and there will be some losses related to that. Okay, now let's start talking about how to consider these losses in our equations. Okay, so suppose that I give you an aircraft and I ask you to calculate its performance. I ask you to calculate how fast this aircraft can fly, or how long it can fly. All these things, we need to know these forces. So we need to know the values of lift and drag coefficients to be able to calculate the forces. Okay, now let's talk about this induced drag concept. So there's nothing new here. It just says that 3D-dimensional wings are bad in terms of these wingtip losses. So when you have a three-dimensional aircraft, due to these losses, the lift will be reduced and drag will be increased. Okay, so these are the two effects. And the reduction in lift is something you have to test experimentally. So if you have a two-dimensional airfoil for which you have this graph, so this is the two-dimensional lift coefficient data. So as I said, the most important parameter that affects this coefficient is the angle of attack. So the horizontal axis is the angle of attack here. And you have such a variation of the lift coefficient. And if you turn this into a three-dimensional design, then obviously the lift coefficient will be reduced. And how much it reduces depends on your aircraft. So for a certain aircraft, if this is the new CL curve, for another design you may have such a curve, and there's no easy way to calculate it. You have to just test it. So you have to put it in a wind tunnel and then see how the actual lift coefficient changes with angle of attack. So that's one change due to three-dimensional effects. The second change is the drag, and we will be talking more about that drag because it's easier to study. Okay, so this is how we study the drag of a three-dimensional aircraft. This is our drag coefficient, and we divide it into two components. We call the first one CD0, and the second term is called CDI. And so the sum of these two components give the actual drag coefficient. So this is what you need to use for your calculations. The first component is called the form drag, or it is called parasite drag as well. This is the drag coefficient when there is no lift. When the aircraft produces no lift, you get a certain amount of drag, and the coefficient corresponding to that drag term is this one here. The second component is called the induced drag. This is the additional drag that forms the difference between three-dimensional and two-dimensional wings, which is caused by wingtip vortices. And these wingtip vortices are created by the pressure difference between the upper and lower surfaces. If you think about that, if there is no pressure difference, if the pressure at the lower surface is the same as the pressure at the upper surface, then there will be no vortices created, right? And there will be no losses. and that means this term will not be there. It will just be equal to 0 in that case. So in other words, the induced drag is present only when there is pressure difference or when there is lift force. Therefore, this drag term is also known as lift-induced drag or drag due to lift. So maybe I can, I don't have the pen, I can't really add any new stuff here. Okay, so let me just restate this part again because this is really important. Okay, so again, when there's a pressure difference, then at the wingtips you will see these vortices which will cause you more drag force. And this is what is included in this part. Okay, so all that effect is included here. And if there's no pressure difference, that means if there's no lift force, there will be no such vortices, and there will still be some drag force, and that drag force is included here. Okay, so we have the drag coefficient has two components. One is which is called the parasite drag. It is due to the two-dimensional shape, and the drag when you get even when there is no lift force. The second part is the increase in drag that you get as you have lift force. Okay, so this is the second part. And for a real aircraft, both of these parts will be there. They will be present, and you need to know both of them for your calculations to be accurate. So this is just the picture showing that. In the 2D case, you have just this part when there's no lift force. And in the 3D case, when there's lift force, there will be this additional drag component. Okay, and if you think about what affects this part, the shape of the wing determines how much increased drag you have, right? So here you see two different wing designs. So this is one of them, and this is the other one, and they will obviously both have different induced drag coefficients because they have different aspect ratios, different shapes, and both of them will have an induced drag coefficient, and they will be different than each other. So now we need to have an equation that will include the effect of this induced drag. So we need to have a mathematical mechanism to incorporate the critical aspects of three-dimensional design into the CDI formula. In other words, we need to have an equation that will give us the CDI values of the two wings shown above correctly. Okay, so if I take this wing and if I modify the wing to look like this one, I need to be able to using my equations, I need to be able to express the change in the induced drag coefficient due to the change of the design. Okay? Okay, so this is our equation, and as I said before, this induced drag component depends on the wing design, obviously. So whatever this expression is, it should include the effect of the wing design. And also it depends on lift coefficient, because when there is no lift, there will be no induced drag. And if there is lift, there will be this term. So apparently, obviously, it depends on the value of the lift coefficient. So for any flying object, total drag coefficient is a function of the lift coefficient. When the lift coefficient is 0, CDI will be 0 as well. And as you increase the lift coefficient, pressure difference will be increased. And as a result, the wingtip force will be stronger. In this case, drag increase will be more. The induced drag coefficient will be a larger value. And from the physics of the problem, we expect induced drag values to increase with increasing CL values. So when CL is 0, CD is 0 as well. If CL is 0.1, then CDI should be something positive. If CL is greater, then CDA should be getting larger. So that's what we expect considering the physics of the problem. And this relation can be studied experimentally. So this is how you do it. You put your model in a wind tunnel, okay? And you measure the lift and drag forces. And using these dimensional values, you calculate lift and drag coefficients. So you do that for one condition, for one angle of attack. And then you repeat the same at a different angle. So here the alpha 2 is a greater angle than alpha 1. And obviously the forces are different, L2 and D2. And you calculate another pair of lift and drag coefficients. And you do this a number of times to see the relation between lift and drag. This is what you'll be doing, by the way, in the wind tunnel experiment, which we will start next week or the week after that. You'll be making these measurements in the wind tunnel. And hopefully you will see the relation here. You will see how the drag coefficient depends on the lift coefficient in a wind tunnel. Okay, so to be able to proceed further, I need to really write down here. So let me just stop here and give a break and go get the pen from my office, and then in second hour I will continue from here. Okay?